Okay, we're going to talk about adiabatic processes today. But before we do, let's review some of the all of the processes we've talked about so far for ideal gases. All right? We talked about isovolumetric processes. That's one in which the volume of the ideal gas doesn't change. Well, we know if the volume doesn't change, that tells us one thing right away, because as you recall, work is equal to the integral of negative p dv from the initial to the final volume, right? If we don't change the volume, we integrate over nothing, and the work done in an isovolumetric process is zero. So that's something worth noting. We talked about isothermal processes. For an isothermal process, that means the temperature doesn't change. Well, recall that the internal energy of a gas, when we derived the ideal gas law, we found that the internal energy of a gas only depended on the temperature. So if I ask you, what's the change in the internal thermal energy of an ideal gas for an isothermal process, you know immediately it's zero, because it only depends on the temperature, and the temperature's not changing. We also talked about isobaric processes. That's one in which the pressure doesn't change. Well, if the pressure doesn't change, we can come up here and look at our work equation, right? And we can say, well, if the pressure doesn't change, it comes right out of the integral. It's really easy to do the integral. And we find then that the work is just P times the change in volume. All right? Yeah, there we go. Let's go back. Isothermal. One other cool thing that we know about isothermal processes, remember the first law of thermodynamics. The change in internal energy is the heat that comes in plus the work done on the gas. If the change in internal energy is equal to zero, if we have an isothermal process, we immediately know that the heat that comes in during the process is equal to minus the work done, right? From the first law of thermodynamics. All right? And an adiabatic process, that's one in which the pressure, volume, and temperature all change, but they change in such a way that no heat flows in. So adiabatic means no heat flows in. What can we learn about, well, if no heat flows in, then we know that the change in internal energy is equal to the work done, right? So if we know how the temperature changes, we know how that will tell us how the internal energy changes, we can find the work done. If we don't know how the temperature changes, and we want to find the work using this integral, we don't really know how to relate pressure to volume yet. We're going to find that out today. All right, so stay tuned for that. There's also, we talked about something called an adiabatic free expansion, and I think I mentioned I really don't like using the word adiabatic for it. I like to just call it a free expansion so that we don't get confused with the reversible adiabatic process. So the reversible adiabatic process up here is one in which the pressure and the volume and the temperature all change together in a regular way, so in a reversible way, that the pressure, temperature, and volume change gradually. They're defined throughout the entire process. Whereas for a free expansion, that's what happens when I have a gas, a box of gas, and I open the lid suddenly, and it's allowed to expand into a greater volume, right? So unlike a reversible adiabatic process, the air is not bouncing off of a piston as that piston is moving. It's not reflecting off of a moving wall. The wall, it's just going along and suddenly the wall's not there. So the particles don't get accelerated or decelerated. They don't go faster or slower. They don't gain or lose energy as they collide with the wall. So it turns out then no heat flows in, but also there's no change in temperature, which means the change in internal energy is equal to zero. And if no heat flows and there's no change in internal energy, we also know then that the work done in a free expansion is zero. But today we're going to be talking about the true adiabatic. Am I questioning your adiabaticity? Oh, man, why is that word so hard to say? We're going to talk about the reversible adiabatic process, not this. So we're kind of done talking about this for today, the free expansion. But before we go and talk about adiabatic processes in more detail, remember, again, work is just the integral of negative PdV from the initial to the final volume. And we were able to use that to show, you know, the work in an isovolumetric is zero, the work in an isobaric is just P delta V. What about isothermal? Just a quick review. How do you find the work done in an isothermal process? Well, work is equal to this integral, but we need to know what to plug in for P, because P changes as we change the volume in an isothermal process. But we can just use the ideal gas law. PV is equal to nRT, right? but t is a constant. So I can solve this for p and have p as a function of v. And I do that just by dividing both sides by v, right? And then I can plug this into my integral. So for p, I'm going to plug in nRT over v dv, all right? But nRT, those are all constants, so they come out, minus nRT. Then I've just got the integral of v initial to v final of dv over v, and as you recall, that's just a natural logarithm, and this becomes the natural log of v final over v initial. So there's just an example using the work integral to find the work done. All right, so for an isothermal process, if I know the temperature and the initial and final volume, I can calculate the work done very easily. Okay, another thing that applies to all processes, right? The work integral applies to all reversible processes. Another thing that applies to all processes is the first law of thermodynamics. And it basically says that the change in internal energy is equal to the heat put into the system plus the work done on the system. All right? Remember, we found when we derived the ideal gas law that the internal energy of an ideal gas depends only on the temperature of the gas, not on the pressure, not on the volume. All right? In particular, for an ideal gas, the change in internal energy is just NCV delta T. Always. Even when we're not doing a constant volume process. Why? Well, really what happened is we said, when we derived the ideal gas law, we found that the change in internal energy was equal to N times F over 2 R delta T, where F is the number of degrees of freedom for the gas. All right? But then it just so happened that C sub V happened to be equal to F over 2R, and so we said, oh, even if we're not doing a constant volume process, instead of writing this, I can use shorthand and just write C sub V, and C sub V really means F over 2R. Okay? And that's always true for all processes in our ideal gas. Okay, so now let's talk more specifically about our adiabatic process. What do we know about them? Well, we need another equation to help us work problems, and I'm just going to give you that equation, and later on we'll talk about where it comes from. So here's the equation. P times v to the gamma is equal to a constant. All right? What is that constant equal to? Well, I just evaluate P times v to the gamma at any point. For example, if I knew the initial pressure and the initial volume, and let's say I knew the final volume, but I wanted to find what the final pressure was. So I'm going to do an adiabatic process starting at some pressure and at some volume, and I'm going to compress the gas to some final volume. What will the pressure be? Well, what that means is I can use this equation. I'm just going to say P initial times V initial to the gamma. That's a constant. That means at the end, P final times V final to the gamma will be equal to the same thing. Okay, but what is gamma equal to? Gamma is Cp over Cv. So for example, and once again, where does it come from? We'll find when we derive it, but just working with it now, gamma is Cp over Cv. So for a monatomic gas, like for example a gas of helium where I have individual atoms that don't form molecules bouncing around, the number of degrees of freedom is 3. There's just the translational degrees of freedom. There's no internal degrees of freedom. All right, so Cv is number of degrees of freedom over 2 times R, right? So for a monatomic gas, that's just 3/2 R. C sub P is just Cv plus R, always, right? And so that's going to be equal to 5/2 R. And gamma then is just going to be 5/3. Just divide Cp by Cv and you get 5/3. For a diatomic gas, like air, we usually think of air as being a diatomic gas because it's mostly made up of stuff like nitrogen and oxygen that form diatomic molecules. So for air or other diatomic gases, how many degrees of freedom do we have? We have the 3 translational degrees of freedom, plus there's 2 different ways it can rotate, right? It can rotate in 3 dimensions, but one dimension is rotated around the axis, which has symmetry and doesn't really count, all right? So we end up with 5 degrees of freedom, 3 translational plus 2 rotation, and C sub V then is going to be 5/2 R, and C sub P is going to be 7/2 R, and gamma for air or other diatomic gases then turns out to be equal to 7/5. How much work is done by an adiabatic process? Work is equal to minus integral P dV, but we also know that change in internal energy is equal to NCV delta T, but that's equal to work plus Q. So I could say, well, if I know how the temperature changes in an adiabatic process, work is just NCV delta T. But if I didn't know how the temperature changed, I could use this integral right here. But to do this integral, I need to know P as a function of V. But I know, as I do my adiabatic process, P times V to the gamma is equal to a constant. What constant? Well, for example, if I know the pressure and the volume at any given point, say like at the beginning of the process, I can evaluate this and it'll be equal to that everywhere. Alright, so then P then is just going to be P initial times V initial to the gamma divided by V to the gamma. That means that the work is equal to negative the integral of pressure, which is this thing, P initial V initial to the gamma over V to the gamma dV. This stuff is a constant, right? So it comes out and I just get minus P initial V initial to the gamma times the integral from V initial to V final of 1 over V to the gamma. Well, I can write that as V to the minus gamma, alright? And then I know how to take that integral, right? It's just going to be, have my constants out front, and then when I integrate this, I just get 1, my exponent goes up by 1, right? And then I have to divide by 1 plus my exponent. So it's going to be 1 minus gamma, V to the 1 minus gamma from V initial to V final, right? And if I integrate, if I differentiate this, this comes down, cancels that, I subtract 1, and I get where I started from. So, yep, I did the integral right. So this is negative P initial, V initial to the gamma, all divided by 1 minus gamma, times V final to the 1 minus gamma, minus V initial to the 1 minus gamma. Alright, so there's an example of using this equation right here to find something useful. We used it to find the work done in an adiabatic process. Why would you want to find the work done in an adiabatic process? Well, we'll talk about automobile engines later on, alright? There's an adiabatic process that goes into there. How much power comes out of your engine? Well, you can use this to calculate it, alright? Now, what if I've got this equation, right? P times V to the gamma is equal to a constant. That's great if I'm changing P and want to find how the volume changes, or changing V and finding how the pressure changes. What if I wanted to know how the temperature changed when I changed pressure adiabatically? Or how the volume changes, I change the temperature adiabatically? Could we come up with a relationship? Well, we could. I mean, if we know the pressure and the temperature, we can find the volume, right? From the ideal gas law. Right? So this relates two of them to a third. So I can use the ideal gas law to come up with versions of this adiabatic equation using different variables. For example, if I wanted to find a relationship with pressure and temperature instead of pressure and volume, I just need to find volume in terms of temperature. So from the ideal gas law, I divide both sides by P, and I find that volume is nRT over P. Then I can plug it into this equation. P times nRT over P, the gamma is equal to a constant. Alright? If I divide both sides by nR to the gamma, alright, there you have it, and then I can rewrite this. P divided by P to the gamma, that's P to the 1 minus gamma times T to the gamma. That's equal to this thing, which is a constant divided by something that's constant. So this is going to be another constant. Right? So that tells me that P initial to the 1 minus gamma times V initial to the gamma will be equal to P final to the 1 minus gamma, V final to the gamma. Alright? You can also find one for volume and temperature just by solving, right? Now I've got this guy here. I want to keep volume, but I want to get rid of pressure. Alright? So I solve this for pressure and plug it in. You'll get another equation. Alright, so that's basically what you need to know to work the homework and work the problems in class. I'm going to go a step further. I'm going to show you how to derive the adiabatic equation. This is going way beyond what you need to know for the homework and exams. But because you will hopefully learn something and with luck gain a greater appreciation of the power of differential calculus, I'm going to show you how it's done. If you want, you can stop right now. You don't have to watch any longer, but I recommend that you watch because it's really cool, it's really slick how it works out, and it'll help you understand the equation and help you better work with math things to do physics. So here we go. What do we know about adiabatic processes? Well, we know that the ideal gas law holds, alright, if we're dealing with an ideal gas. The ideal gas law, however, has three different things. So we wanted something that relates like pressure to volume without temperature around, right? So we need to somehow get rid of this third parameter. What other equation do we have? What other things do we know about our ideal gas? Well, we know the first law of thermodynamics. The change in internal energy is Q plus work. And specifically for an adiabatic process, Q is equal to 0, so we can get rid of that. All right? And we know that the change in internal energy is just NCV delta T, and that's going to be equal to work, but work is minus the integral of PdV. All right? So we can use this. This has got temperature, pressure, and volume in it, and maybe we can use this to get rid of one of those. We have a problem, though. First of all, we've got delta T instead of T, and we've got this integral. Let's get rid of the integral first. So this is V initial, V final, right? How do I get rid of an integral? An integral is the opposite of a derivative, right? It's the antiderivative. So let's take the derivative of both sides and get rid of that integral. What am I going to take the derivative with respect to? I guess we're going to take it with respect to volume, right? So NCV d delta T with respect to volume then is going to be equal minus pressure. Well, how the change in temperature changes is just how the temperature changes, right? So we can get rid of the delta, and then we just have NCV dt is equal to minus P, and I'm going to bring the dV over here, all right? Right? This may seem weird to separate our derivative into two pieces, but the dt is just a little change in temperature, and dV is just a little change in volume, so we move them to the other side, all right? Okay, but then we have a problem. We have this, but now we have things in terms of dt and dv instead of t and v. We're going to have to integrate eventually to get rid of that, but if I integrate, I get back to where I started from. So instead, let's take a derivative here and try and make this look more like that, all right? So I'm going to take the derivative of this. I'm going to take the derivative of my ideal gas law with respect to, I don't know, something. Just any random thing. So x. X could be volume, could be pressure, could be like time. You know, I'm doing some process, whatever. I'm just going to take some derivative with respect to some unknown thing, all right? Doesn't matter what I'm taking a derivative with respect to, all right? I'm just going to take derivative of both sides, all right? And when I do that, I can use the product rule, right, for derivatives. This is just going to be P times dV dx plus V times dP dx. Hopefully you remember that from calculus, all right, from differential calculus. And here, n and r are constant, so this just becomes nr dt dx, all right? Now I'm going to get rid of my dx's, right? This is just a little change in volume when I change my whatever. This is a little change in pressure when I change my whatever. This is a little change in temperature when I change my whatever. I'm just going to get rid of these things here, all right? And I'm going to say when I do some little tweak to my system, I get a little change in the volume, I get a little change in the pressure, and a little change in the temperature, and they're related by this equation right here. Well, notice, all right, I wanted to get rid of dt, and here's an equation that can help me get rid of dt. So I'll come over to my first law of thermodynamics process over here. I'll solve this for dt, and this is just minus p dv over ncv, right? And I can plug that in over here now, and I get p dv plus v dp is equal to nr times this thing, minus p over n dv over cv. There we go. Okay. All right, now I'm going to combine some terms here. I've got a pdv here and I've got a pdv here, and these n's cancel out. And so this is, I'm going to take this over to the other side, and I'm going to get 1 plus r over cv pdv plus v dp equals 0. Okay, we're starting to get somewhere, all right? This is just a constant. I'm going to call that gamma to make life simple, all right? So I've just got gamma pdv plus vdp equals 0. I need to do an integral now to get rid of these d stuffs. But how am I going to do the integral? I can't, if I just integrate this, I can't integrate pdv because I don't know what p is as a function of v. I can't integrate vdp because I don't know v is a function of p. All right? But what I'm going to do, since I only have p's and v's, I'm going to get all the p stuff to one side and all the v stuff to another. And then I'll be able to integrate. All right, so I'm going to say right here, I've got gamma p dv. I'll take this guy to the other side, and that's going to be then equals minus v dp. Then I'm going to divide both sides by p times v, so I can get all the p stuff to one side and all the v to the other. So I'll divide by pv, divide by pv, and over here the p's cancel out, over here the v's cancel out, and what I end up with is gamma dv over v is equal to negative dp over p. Now I can integrate. I know how to do this. I know how to integrate dv over v. I know how to integrate dp over p. What are my limits? I have to have corresponding limits. So I'm going to integrate here from the initial volume to the final volume. All right? The pressure that corresponds to the initial volume is the initial pressure. So I'll put initial pressure here, final pressure here, and when I integrate that, what am I going to get? I'm going to get the gamma comes out, it's a constant, and this is just dv over v. I integrate that, I just get the natural log of v, and evaluate my limits. I get v final over v initial. Over here, the minus sign comes out, and I get the natural log of p final over p initial. All right? So once again, we already did that. Got ahead of my notes. So what we had was gamma natural log of v final over v initial is equal to negative natural log of p final over p initial. All right? Properties of logarithms, I can take some constant multiplied out front and turn it into an exponent inside. So I'm going to get natural log of v final over v initial to the gamma. Same thing, I can take minus 1 and turn it into an exponent over here, and this becomes natural log of pf over p initial to the negative 1, which is p initial over p final. Then I can exponentiate both sides, get rid of the logarithms, and I find then that v final over v initial to the gamma is equal to p initial over p final, or p final v final to the gamma is equal to p initial v initial to the gamma, or in other words, p v to the gamma is equal to a constant. Alright, so there it is. I derived it. We're done. That was pretty cool, huh? And that's all we have for you today.